Hi, it's great to be back here. I was at Craft 3 years ago. I just want to admit, I'm not going to be here tomorrow because I've got to go to Barcelona because there's a Formula One race. So this is the only slide I have on that. But I now spend some of my time at Formula One races trying to talk to executives about how they should speed everything up using F1 as an example. Anyway, so that's the only slide I have about Formula One. I'm going to talk about other things that need to be sped up. So the way I see it, there's 3 stages that we go through as we're trying to innovate. The first thing is trying to get going really fast to get small things done quickly. The next stage is really getting large-scale things built quickly, a lot of the sort of net new greenfield kind of applications. And the third thing we're seeing is a lot of customers doing data center replacement and moving critical workloads out. And again, typically, if there's a data center replacement, there's a deadline. Right? The lease runs out in 2 years or something, and that 2 years comes up pretty quickly. So those are really deadline-driven things. All of these are pathways that are involved in speeding everything up. So I'm going to talk about these 3 sections. So here's the basic thing. Don't add innovation to an organization. You don't hire a VP of innovation and become more innovative, although people seem to try that. You get out of its way. So what's the metric for innovation? And really, I think this is the key thing. You do some work, and how long does it take before that work is adding value to a customer? Is it taking you months? Is it taking you days? Or have you got a continuous delivery pipeline that's delivering, you check in some code, and a few minutes later, it's running in production? Now, there are quite a few companies running at that speed nowadays. And this really comes down to this basic thing. There's no economy of scale in software. Bundling more things together slows you down overall. Having lots of smaller changes is better. So with lots of small changes, we need an automated continuous delivery pipeline because we don't want to do lots of things manually. We need tagging. We need to tag the versions. We need feature flags. We need A/B tests so that we can control what happens. And need really rapid, cheap builds. So I was talking to somebody about doing this, and this is all great, except our Java build takes 11 hours. So I'm not going to continuous delivery of once every 11 hours. So I said, okay, so I think there's some technology changes here. Instead of having a monolithic Java build, why don't you do sort of microservices in Go? Because if you type Go build, it returns in less than a second most of the time. And even microservice, it's going to be breaking into small pieces. So then, you can make technology decisions to go from your 11-hour build to a few seconds build. So that's one of the things that you just have to think, go figure it out. So we want to change one small thing at a time because it's easier to tell if it breaks. It's easier to roll back to the previous version. And it's easier to measure that time to value. You've got a precise measure. I make one change, it delivers. I've just got 2 precise endpoints. If my 6 months work by hundreds of people is when I create the value and it delivers in one go, then it's kind of fuzzier. Like, is that when you started creating value, when you ended creating value, and what about the work that you did that got deleted before it even reached production? What happened there, right? So we need to decouple new code from new features. We want to incrementally change the system with lots of small, safe updates, and then just turn on features for testing, and when it works for everybody, turn it on for everyone else. So that's kind of the mechanism. So small changes get less risk, faster problem detection, faster repair, less work in progress, less time merging changes. So you just got less, reducing work in progress is really the core thing here. You end up happier developers. If you change the world every day, you're going to be happier than if you do some work and think maybe in 6 months somebody will use this if it doesn't get deleted before then anyway. And you just get faster flow. So how do we get there? First thing is measure time to value. If you're a manager, you say, what is the time to value of each of the teams that work in this organization? And do the work to figure out how to measure that. Then you can see which teams are running slowly. You can also see which teams with the time to value is getting longer and longer and longer, and which ones are getting faster. And it's not really about how fast, it's just you want to be going faster, you want to be improving. As soon as you start measuring something, it'll start improving. That's one of those management things. Learn to do small things quickly. Don't try to automate the process for your most critical, biggest workflow. Do it for something easy and small. So have a fast path, a quick process for doing stuff, and leave the old way of doing it alone for the moment. Just start getting some quick wins in. And measure cost per deploy, because if it takes you huge amounts of CPU time and hours of build time, that's a problem. So you want to reduce that. You want to reduce the number of tickets. I asked somebody I was working with, and they said, how many tickets per deploy do you have? And they said, 600. Takes 6 months. We deploy every 6 months about 600 tickets. Okay. And how often do you want to deploy? Oh, several times a day. Okay. So we need to get that down to 1 ticket, which is a tracking ticket that is automatically updated as that code flows through the production pipeline and ends up going through all the test and production stages. And you don't have time to have 10 meetings a day for the 10 times you deploy today personally. So there can't be any meetings. There are still meetings to discuss what's happening, but they aren't in the flow of a deploy. So there's a few good books to look at. Lean Enterprise, been out for a little while. Hypothesis-driven development. It's probably the most accessible book that describes how to do all this. By one of the authors of that, more recently, Unlearn. You've learned all these bad habits. They worked for you in the past, they're not going to work in the future, so you have to unlearn them. So Barry O'Reilly came out with this book. This is all more hard work to read, but it's the theoretical basis for why this works. And then project to product. And if you don't have any projects, you don't need project managers. And I'm sorry if we have project managers in the audience, but you really should try retraining into something else. And if you're in a company that's hiring project managers, probably just stop hiring more of them and redeploy the ones you've got. Because if you're doing continuous delivery, you're doing product work, and there aren't any long projects, and there's nothing. So the people that will resist this change most are the project managers, because they see their jobs going away. So that's a whole other layer of management problem. That's not a technical problem. Survey data showing that companies that go fast have better productivity, they have better outcomes in the market, they grow faster, they have higher stock prices, all of these kinds of things. There's some correlation work here to show it really works. Anyway, so what we're trying to do, learn to do simple things quickly to unblock innovation, avoid any really complex one-size-fits-all processes. So the best architecture to do this today is actually minimalist, messy, and inconsistent. So that kind of ties into some of what Stefan was saying in the previous talk. You still have guardrails. You still have to say, whatever you do, it has to be secure, scalable, and available, but I don't care what framework you use, I don't care what language you wrote it in, I don't care how you delivered it, as long as it's scalable, secure, and available enough for the purpose it needs to be. So that's a sort of a more guardrail-based architecture which is designed to evolve and absorb all of the latest technologies as they come along. And if you want everything to look nice and tidy, you're going to slow everything to a crawl. That's the problem I keep seeing. But this really supports low latency continuous delivery. So that's the sort of time to value piece. Now, we started talking about architecture. What kinds of architectures are we building for the new systems? And they're distributed systems. They are highly scaled. They're distributed for availability. They're cost optimized, very high utilization. This is the difference between the data center, where it's kind of hard to get much over 10% utilization for the systems because you need extra capacity for peaks, and they go quiet at the weekends and all these other things. In the cloud, you scale down to 0 when you're not running something. So you can keep your utilization many, many times higher, like 40 to 50% utilization average across all of the machines in the cloud would be a good target. Right? That's achievable. So that means you can run on average on a quarter of the number of machines that you would have in the data center on average, but at peak you have more machines than you had in the data center because you hit a peak, but you only need it for the peak, okay? And this is really the basis of a cloud-native architecture. It's elastic. It's the most fundamental piece of a cloud-native architecture. So here are the principles. One thing is you pay as you go the month after you use the resources. Very different to a data center where you pay up front for 3 years worth of depreciation. Self-service, no waiting, API-driven, globally distributed, zones and regions for availability models, very high utilization, and you deploy code by creating a new machine, not by updating the machines you've got. And those are the patterns that really come in. So that brings up another question right now. So you can build cloud-native models containers, or you can do serverless, or you should do both. And I'm going to really say you probably need both, but I'm going to say serverless first, and I'm going to run a little story here to try and show why. So let's say the user need is a sort of a spaceship that looks vaguely familiar. You want a toy spaceship. This is just an analogy here. I'm trying to build a model spaceship. How would I do that? Well, I'd design a prototype using AutoCAD or something. I'd carve it from modeling clay somehow, make some molds. I'd produce a bunch of parts, and then I'd discover they don't fit together and go back and design them again and do all this kind of stuff. Try to eventually get something I can assemble. And then finally, I've got a toy. I can sell the toy. This is cool, right? This is the traditional development. It's sort of waterfall-y. It takes a long time. That's the way we custom build things, right? So here's another way of doing development. And I noticed that, I saw there's a Bugatti Veyron you can get here, right? How long does it take to build a real Bugatti Veyron? Like, I don't know, it's probably a month or something. Months, even not including the design time. How long does it take to build the Lego one, right? So rapid development, we get a big bag of Lego bricks, we get some instructions, we take a few hours, and this is my favorite this is actually a PowerPoint animation, and it's my favorite one we ever did. Lego, I don't even know how we did that. I told somebody, I just said, make a spaceship out of Lego bricks, and I sent it to a graphic design company, and they made this work, and I want to just do that again, because it's cool. Lego bricks falling from the sky. Right, so in a few hours, you've got something that looks roughly the same shape as the thing that you would custom build, but it lacks detail. It's got sharp corners on it. It's recognizable. Kids would probably still play with it for about the same length of time as the proper toy. They probably play with the box it came in for longer than that, but that's just kids. It's easy to modify and extend. You can add things to it much more easily than the custom one. So you take a group of these bricks and say, that really isn't pointy enough. And so we build a custom brick. And a lot of Lego things you see, each time they build one of these, they make one or two new custom bricks to just add a little bit more extra sort of customization to it. And that's a more specialized component that they can use in other places as well. So if we look at the two side by side, instead of a full custom design you're building from bricks, instead of months of work, it's done in hours. Custom components, they're fragile, you have to plug them together, it's debugging. Standard components are much easier to plug together. You've got too many detailed choices and long decision cycles, whereas if you're building something out of bricks, you're highly constrained, and a lot of discussion goes away because you can speed up the decision making because it can only be certain sizes, right? You don't have to choose. The scale is sort of set by the size of the bricks. So if we look at this as sort of containers versus serverless, containers is very custom. You can build anything you want, lots of choices. You can spend forever debating which container scheduler you should be using. You could have finished building your entire application in less time it's spent than arguing about which version of Kubernetes you should be using. But there are times when you get through, you build your rapid assemble your thing out of building bricks, out of using serverless. Then you say, this piece of the system needs to be polished a bit. It needs to be lower latency. It's running long-running compute jobs, or it's going to be very predictable high traffic, and I can optimize. So you take something that you rapidly prototype in serverless, and you build a new service that you'll build a new custom brick, and that's when you go to doing the sort of the more custom work, and you do your container-based application. So this is kind of what I'm seeing as the best practice for the companies that are building things ridiculously quickly, because they really are building new applications in hours as rapid prototypes in serverless, and then they're optimizing them to fit the need by adding a few services and plugging other things in. So I'm going to talk a bit about a few other aspects. Some about observability, some epidemic failure modes, and a bit about automation. So what is observability? It comes from 1961. A system is observable if the behavior of the system can be determined by looking at its inputs and outputs, right? That actually makes some kind of sense. This is a model, so, this applies, originally this was for control systems, like physical control systems, machinery, but it actually applies just as well to software, because all of these things are approximate models. Your model of your control system is always going to be slightly approximate, and it's approximate whether it's a physical or a software system. So what do these models look like? Here's one. This is the STPA model. And I think this is a really interesting model. The thing at the bottom is the controlled process. That would be the application you're running. Above it, there's some kind of automated controller which is watching over that and trying to control the behavior of that process. And at the top, there's a human being who is poking at that control system and probably messing it up occasionally. And this is a bit abstract, so let's turn this into something you might recognize. Let's say the thing at the bottom is the sign-up flow for a website. Like, pretty much every website in the world has a sign-up flow. So customers are sending requests, and eventually the sign-up flow spits out a new customer, right? Okay, you filled in all the things you were supposed to fill, and you want to make new customers come out of this flow, right? And that's running on it's a microservice of some kind. It's running on an autoscaler, right? So if you have lots of customers arrive, you want to scale up. So the next thing up, the control system for this is an autoscaler algorithm, and it's got a maximum and minimum number of instances that it'll move between. And it's looking at the CPU utilization, and if the microservice gets busy, it adds some more, and if it gets idle, it drops them, right? Pretty standard. And at the top, there's a user who's watching the throughput of the system, and if the new customer throughput suddenly drops or does something bad, they'll go, hey, what's happening? And go, and maybe I need to set the maximum higher, or something is broken, right? So there's the humans that are tracking the system, making sure it behaves right. So STPA is about understanding the hazards that could control this. So maybe the system doesn't run out of CPU, it runs out of memory. Now the system, the autoscaler is going, no, I'm fine. You're not out of CPU, you're out of memory. But the user doesn't understand that it's out of memory because they're not looking at that. So the model of the control process that's in the human's head is really important. It's sort of documentation, it's a bit of training. You have a model for the thing that you're managing. And you have a model for the way the control loop, the way the autoscaler behaves. And a lot of the problems we have with failures in systems are because the model in the head of the operator, it doesn't correspond to the model, the actual behavior of the controller, and is not properly reflecting the behavior of the process underneath. If you look at those plane crashes recently, the pilots didn't understand that there was an automated system that was trying to prevent stalls and was nosediving the plane. They didn't understand. The model they had in their heads didn't correspond to the behavior of the system. And that was the fundamental reason why they crashed. Okay. So, observability, that's a control system model, and it's actually, I think, a reasonably interesting way of looking at it. So if we look at a monolith that's got a bit of logging going on in the background, that's got some observability. You can see roughly what it's doing, but you can't see why it's doing it, because monoliths have too many behaviors inside them. If you have tracing, now you can see the flow of requests through the monolith. Now you can kind of start figuring out, okay, this is why it's doing that. It's much more observable because you can see the behaviors flowing through. If you get a microservice that does one thing, then it's more observable, inherently more observable, because you ask it to do the thing 10 times, it should do roughly the same thing. But microservices quite often have some internal state, or they respond differently based on the state that, based on the stored state that they pick up from the storage systems behind them, databases. But if you have a function, like a Lambda function or just some functional programming code, code written in a functional language with no side effects, the nice thing about a function with no side effects, it should do exactly the same thing every time you ask it to do that. So they are extremely observable. You don't need to log the internal behavior of a function because it's a defined thing. So that's just another way of thinking about observability. So let's talk a bit about failures. A lot of people assume failures are independent, but they can be correlated, like a few things, this dies at the same time as this dies because they're actually related. Or there's epidemic failures where everything breaks at once. Here's a few epidemic examples. A leap second bug that takes out all versions of Linux that have the wrong, unlucky patch level at once. A memory leak in an agent. So everything runs fine until the agent gradually takes out every instance that's running that agent. A cloud zone or region failure takes out a whole bunch of systems at once. DNS failures, well, the easiest way of breaking almost anything is to get at DNS and break it. Or deploying a security configuration globally and automatically that breaks everything in the world at once. Those are good ways of breaking things. So how do we deal with that? So what we need to do is quarantine them, because there is an epidemic, you hear about quarantine, right? That's what you do. You try and contain it. So maybe, if you're worried about Linux bugs, maybe you can deploy that Java app on Windows just the same. So you could, Linux is having a bad day today, I'm just going to redeploy everything on Windows. Because the Windows code base is sufficiently different to Linux that you hopefully don't have all the same bugs in it. Although I think the latest version of Windows includes Linux, so that may not work so well. Maybe BSD or something, but I think you get the point. Multiple monitoring tools so that you can see when something breaks or you've got some diversity in there. Cross-zone, cross-region replication for clouds. Multiple domains and providers for DNS. And limiting the scope of deployments. You deploy to one zone or region at a time, you check everything's okay, and then you walk it around the world. So global simultaneous deployments are pretty much always a bad thing. So you need to manage diversity to contain an epidemic, basically. So that's kind of that cloud native bit. And I'm going to talk a bit about these strategic workloads that we see moving to data centers. And here's an example, it's a customer example. This came up recently. I think I've got some notes here reminding me of the actual things here. I could get the data right. Where is it? I think there's 30,000 locations that Volkswagen and its partner ecosystem has. 30,000 locations. This plan here is to use the cloud to integrate and automate and replace the technology that does this whole worldwide huge conglomerate, right? This is an enormous deal. There's a lot of data centers that get replaced by the cloud as part of this deal. It was announced a few weeks ago. You can go find the press release. And we're doing this together, and we're going to build a platform that we're then going to share with other major industrial manufacturing companies. So this is just one example. There are similar deals with airlines, with healthcare. It's going on banks. So these migrations are underway now for travel, finance, healthcare, manufacturing, lots of places. People are basically deciding, I can't build a data center that is better than what I can just get off the shelf by opening a cloud account. So I'm going to stop trying to do that. And then they say, well, we've got like 3 years on the lease, so we're just going to run out the clock, and we need to be out of there in whatever it is, 2 to 3 years, something like that. So this brings up all of the other things. There's lots of strategic workloads here. Who here has a backup data center? You got a few of you? Okay, most of you. Who here doesn't like putting their hand up? Okay, all right. How often do you fail over apps to your backup data center? The usual answer is like once a year because the auditors make us, is the normal answer, or never is the other answer. How often do you fail over the whole data center at once by pulling the plug on it or hitting the... That really never happens unless it happened, or never happens in a planned way, right? So I call this availability theater. You've invested all this money in a backup data center and you're not really... You did it because you were told to, not because you're really getting value out of it. So we have this fairy tale. Once upon a time, if everything works perfectly, we have a plan to survive the disasters we thought of in advance. Not a good fairy tale. It'll keep you up at night because it doesn't work out very well. So here's one. Somebody forgot to renew them. Think of the company you work at and thing.com or whatever it is, .hu or whatever your local domain. Imagine that isn't available anymore. How much of your systems still work? If you're a SaaS vendor, your product's offline, But in this case, all of their internal email was offline. What was left of this company was the CEO apologizing on Twitter for about 2 days before they got it all back together again. This was a major SaaS provider, right? Not a happy thing. It's pretty easy to break DNS. This has happened to everybody. I don't know a single person or a single company who's worked in IT who has not seen a certificate timeout take something out, and it happens every week. I think the British mobile phone system from one provider went down because somebody at Ericsson forgot to update a cert, and there's a huge fine thing going on there around this. So it can be very expensive to do this. We spend a huge amount of effort at AWS tracking these stupid certificates and managing the process of updating them and making sure none of them snuck into the code when no one was looking. I have a friend that works in New York, and it turns out computers do not work underwater. And when the water's gone away, they don't work when they're full of mud and sand either. So he spent a happy few months building a completely new data center that was not in the basement of a building in Jersey City anymore, because Jersey City is at sea level and basements. That wasn't good. Anyway, hopefully you won't go to work tomorrow and go, whoops. Anyway, so what can we do about this? The most generic thing you can do about availability is get really good at detecting and responding quickly to whatever happens, right? It's the human side of being on the ball, noticing that something went wrong, and then being well organized about how you respond to it. So this will save you from an arbitrary thing going wrong. It's the best training you can do. Chris Pinkham was the guy that built the original EC2, and this is the principle a lot of Amazon works on. This is a good paper you should read. The network is reliable is the first fallacy of distributed computing. So spoiler, the network is not reliable. Drift into Failure is an interesting book. If you really want to, I tell people not to read this book on aircraft because it contains lots of stories of planes crashing. And after a while, I actually wrote a slide deck of the plane crash while I was on a plane on the way to go to Chicago. So if you find my talk from Go to Chicago last year, I wrote that entire deck, and it's basically chapter 2 of this book as a keynote presentation at the event. Everything went fine in every possible way, and then a lot of people died, and then but that was the first time that particular fault had happened in 9 million hours of operation and 30 years. So that was a huge success that it hadn't happened before, right? Even though people died. So you have to kind of think about these things that they haven't happened, so people start to believe it will never happen, and then it happens, right? So there's a problem. Release It by Michael Nygaard. Lots of good ideas in this book. Bulkheads and things. The version 2 is definitely got some good new ideas in it. And this is a new book. I mentioned STPA before. Engineering a Safer World. It's a book I've come across more recently, and I've been trying to incorporate the ideas from it more. You can go to the MIT website and find there's a handbook, there's a bunch of recent talks. If you're really into building really safe systems, you have to kind of really dig into this and understand it. So this is I'm still trying to figure out exactly all these techniques myself, but this is kind of my latest piece. So, in the past we had disaster recovery, we had 2 data centers, we'd fail them over, and hopefully it would work eventually. Nowadays, we have more chaos engineering going on, where we're trying some things out and automating it a bit. But in the future, we just need to have it so that chaos engineering isn't a strange thing that just the unicorn Netflixy people are doing. It becomes baked into the way that all of the banks are running their things, and all the airlines are running their things, and all of the healthcare companies, because we depend on those to work. And everybody needs to do this. So it can't be a specialized thing. It has to become really baked into the way everything's built. And that's kind of the area I've been focusing on recently. So here's the history of chaos engineering. Jesse Robbins really kicked it off in 2004. He used to go around turning off data centers at Amazon. At Netflix, Greg Orzel wrote the first Chaos Monkey. The Chaos Monkey was there to enforce a design constraint. It was an architectural design constraint. We wanted every developer to build an auto-scaled stateless service. So we just went around deleting instances because then the autoscaler was supposed to put them back. And then if you put some state in the service, you'd lose the state. So it sort of forced you to put the state in a database at the end of every request and to put everything in an autoscaler. So that was it. It wasn't about trying to break things. It was to enforce the design constraint, the architectural constraint. We open sourced it in 2012. I was at Netflix then. And then Colton Andrus, who was working at Amazon for a while and then again at Netflix for a while, founded Gremlin, which is a company that makes chaos engineering tools. They published a book. And there's actually quite a few startups now in the chaos engineering area. This is the book. Lots of good examples in this. And I put this in 4 layers. You've got to have a resilient infrastructure. You've got to be able to switch between multiple ways to get things done, and that switch has to be incredibly reliable and be well tested, which is, the problem is that, think of that disaster recovery as the switch from one data center to another is the least well tested piece of infrastructure, of code in your entire system, and it's the piece you want to work most under stress. That's a bad combination. The application should survive random things happening to it without just crashing. And the people need to understand, so this is game days, they need to understand how to handle failures and outages. So this is what the chaos engineering team does. It's also, from the security point of view, what the red team, security red team principle is. So you've got 2 teams who are trying to prove that your system is resilient from security and availability attacks. And the real thing here is you can only be as strong as your weakest link. And you need a dedicated team to find that weakness. Because if you're sitting saying, you know, I'm fine, my job is to make it safer, that's one thing. But if your job is to find the weaknesses, that's a completely different set of incentives in the system, right? And you're much more likely to find the problems that way. And the failures are a system problem. If a system fails, it's because it didn't have enough margin to absorb whatever went wrong. The fact that a human pushed a button isn't the cause of the failure. The cause of the failure is the system didn't have some kind of fail-safe on that button, or did you really mean that, or please do not push this button again, or something, right? There should be some better way of doing that. So what you need is experienced staff who've been through outages, they know how to behave on a call, they know what to do, they've done some game day work. You need robust applications and dependable switching fabric and a redundant foundation underneath. So cloud provides the automation that leads to chaos engineering. It's really hard to do in data centers. That's why data center failover is so difficult, because data centers drift, they're out of sync, and when you fail over, you find the wrong version of something somewhere, and it doesn't quite work right. The cloud is much easier to manage the consistency of 2 cloud regions for failover. And these fragile and manual disaster recovery processes can be standardized and automated. And this is kind of the path we're on right now, building a lot more automation around the tools you need to do disaster recovery, failover, and things like that. We're working on some tools at Amazon. The customers are building it. We're starting to document the patterns that do this. Particularly, we're working on some core banking applications in the US. And we recently published a paper under the financial services section of the AWS site on resiliency for financial services. A lot of detail there. I was co-author on the paper. So it's going to move from a scary annual experience to continuously tested resilience. All right, so that's what I had. I think I've got a few minutes left for questions, so we can put up the tweet, whatever the question thing is, and see what they got. Oh, there we go.
Slido. Yes, it's Slido. Twitter is for later, for the break. Yes? Now let's do some Slido activity. So, we do have a couple of questions. In theory, going from monolith to microservices is good, but how do you approach this for a very large code base developed in 10, 15 years?
Okay, that's the normal state. Pretty much everyone's got a large code base developed over a long time. It's a strangler pattern, which we've You break off little pieces. You stop adding new things to the monolith. You start creating new things by creating services around it. But then you start picking pieces of the monolith out. What I typically do if it's a web service monolith is put an API gateway in front of the monolith, and then you can pretend that the monolith is still there by having like one unified endpoint, but the API gateway will route traffic to the microservice that now does that work, and instead of sending it to the monolith. So you can stay compatible and do that. The other thing is the database behind is usually the other half of the monolith. You've got a monolithic schema database, and it's a big tangled mess, and you have to start untangling the database and pulling out each materialized view into its own data source to get a back-end for front-end kind of model. So untangling the monolithic code base, but also untangling the schema in the database that's behind it. And often this starts off with, once upon a time it was a nice clean Ruby on Rails system, and now it's turned into this big hairy monster, and you have to kind of pull pieces out of it to get it back to make sense. I mean, there are other challenges in keeping all the multiple databases in sync and things like that, but they're actually easier to solve than trying to update a monolithic data schema or a big complicated monolith itself.
All right, thank you. How do you convince management to move from the mindset of the bi-weekly releases to daily or hourly releases and amount of time, resources it takes to release changes to production?
If your bi-weekly releases are mostly okay, it's the people releasing every 3 months to 6 months that have the real problem. It may be that bi-weekly is fine, but if you've got a competitor that's updating 10 times a day and you're updating every 2 weeks, then you'll fall behind. You can't learn enough about your customers and learn enough about the market and learn about what's going on. So you'll just start to fall behind. And that competitive getting left behind is the fundamental thing that the managers want to solve for. And from the sort of business product management side, they go, I have all these features I want to roll out, and it's taking too long. So I want to get new features to customers faster, and if they see another company going faster because they're doing continuous delivery, that's the driver. It's business value is going to be delivered faster. And if you're delivering every 2 weeks, you've got a lot of work in progress that's not value. You're not getting value from the work until it's reached the customer. So your 2 weeks worth of work in progress is worse than 1 day or an hour or 5 minutes, right? You want to reduce that.
All right. In a large number of cases, cloud makes sense, but at what point, volume, security, etc., does it make sense to have your own data centers?
It makes sense to have your own data centers when you need to be local to something, like in a factory, or or in a particular geography where there isn't a cloud region. That's the primary use for having your own data centers. There's definitely a scale that some companies get to where they're just big enough to run their own things, but then they're effectively running a cloud. So the largest companies in the world are capable of running clouds, and they're capable of running their own data centers, and that's fine. If you look, Facebook runs its own data centers. They've got enough scale, enough automation. They run those data centers like a cloud for themselves, but that's a huge company. I think most people, if you look at the technology that you can get in a cloud, machines with huge GPUs and 100 gigabit networks and enormous flash storage arrays, those things just turn up in your cloud. If you're using a cloud, you have to go procure them if you're building your own data center. And after a while, you just give up trying to do that. All
right. Oh, please don't make fun of me. I don't know how to pronounce these K8s. What about K8s and deploy on multi-cloud providers?
So that's Kubernetes. Kubernetes is, if you need to deploy across multiple clouds and on-premise, Kubernetes is currently the best way to do that. All the cloud providers have ways to run Kubernetes. They run a compatible, there's a certification process, which means that the version you run in your data center, applications should be compatible. So there's no, if people start modifying Kubernetes and making it different, you're actually losing a lot of the value. The fact that it's common is the real value there. And AWS is running the majority of all the Kubernetes in the world, according to a bunch of surveys over the last few years. And we're running some of the largest clusters for some of the largest customers as well. So we've got huge deployments on Kubernetes right now. It's also a service which we provide in every region of AWS. Every new region that launches has Kubernetes in it at launch. And there are 1 or 2 regions that we're still catching up with. But we have 21 regions in the world now, and I think we're in almost all of them. We're working still on China, which is a little harder to deploy in China, but there's a few places we haven't got to. So it's going to be just a standard feature of AWS in every region.
All right, we have time for the last question. Are there any cloud standards? Is it easy way to switch cloud providers?
Well, it's easier to switch cloud providers than to switch data centers and data center providers. So there's once you get out of a data center, you have much less lock-in than once you're just in the cloud at all. One of the things is that the bandwidth between clouds is vastly higher than the bandwidth between data centers. If you think about you're trying to, if you go to the Virginia region, there's an AWS region there and there's an Azure region there, and the bandwidth between them is ridiculously high, just some enormous number. And buildings are pretty much next to each other, so the latency is really short. So if I want to move 10 petabytes of data from AWS to Azure or vice versa, I can do that fairly easily. When you look at a data center and you try and migrate petabytes of data out of it, it takes a long time. So it's relatively easy to move data. Kubernetes is basically the cloud standard for if you want to switch providers or if you need to deploy into multiple clouds. So it's relatively easy to do that. I think the differences come with the sort of geographic region. There may be only one provider has a region in, say, France or something like that you want to go to. And with AWS, typically there's a broader set of services and more depth in those services. We're sort of bigger and we've been doing this longer, so you may depend on features that aren't in all the different cloud providers. But those features are there because customers asked for them and we get to use them. And so that's kind of eventually a few years later, maybe the other cloud providers will have those features. So that's the other thing is if you wait long enough, things get more portable. But if you want to go faster and get things built quickly, then AWS, I work there, but we're the lead provider and we're basically moving faster with more customers than anyone else right now.
All right, thank you very much.
Thank you.